All right, on this next example of a coupled system, we're going to look at what happens if you have a pulley. So this pulley here is used to take the string, which is attached to the big M mass, and connect it to the little m mass. And so the question is, what exactly does a pulley do? So a pulley can function to change the magnitude and the direction of a tension force. But if we have a pulley that has a negligible mass, that means the inertia of the pulley is really negligible. You can ignore it. And in that case, what a pulley does is it changes the direction of the tension, but not its magnitude. So if I were to pull on the string with 10 newtons to the left here, and the string is wrapped around a pulley, the string would pull with 10 newtons to the right on the bottom. It would change the direction that the tension is acting, but it would not change its size. So whatever tension I pull with here, that will be the same tension in the string down here, just pointing in a different direction. Okay? So that's what a pulley is going to do. So when we look at this system here, what this pulley is doing is changing the direction. There is tension in this string. The tension in the string pulls on big M to the right. The tension in the string, the same tension, pulls on little m upwards, okay? So we're going to use that to solve this problem. All right, so the first thing we have to do is build a free body diagram, and we got to do this carefully. So we are going to look at this mass first, capital M, all right? So here we go. There is my mass, capital M, and I'll label it capital M. This mass accelerates to the right because it says the system is in motion, and we want to know what is the acceleration of the system. So big M accelerates to the right, so I'm going to call that direction to the right the positive x direction. Remember, we get to choose the coordinate systems. We're going to make them so that the objects accelerate in the positive x direction. If that's the positive x direction, then the y direction is perpendicular to it, like that. Now we've got to draw all the forces acting on M right here. The obvious force is gravity. It points down, and its magnitude is capital M times G. There's a force pushing up on this mass due to the table. That is a normal force. It's the same size as the downwards force, and we'll label that F sub n. The tension in the string is pulling to the right. We'll label that T. And because there's friction between the block and the table right here, there's a force to the left opposing its motion, and that's the friction force. So those are the forces that act on this mass right here. Now, we need to really solve a separate problem, because for this problem, it's going to accelerate downwards. So here's my free body diagram for little m. I'll label it little m. So here's my object. There's a downwards force due to gravity pulling on little m, and it looks like that. So we're going to, since it's going to accelerate downwards, we're going to call that the positive x direction, and that makes that the y direction. It's a little goofy, but you can make coordinate systems any way you want as long as they're perpendicular. So there is a downwards force on m of magnitude little mg. There is an upwards force. What is pulling up on this mass? It's the tension in the cord. So it looks like that, and that's T. So there are my two free body diagrams. For this capital M mass, it's accelerating to the right, so that's positive x direction. For this little m mass, it's accelerating downwards, and so that's the positive x direction. Okay? All right, so now, here's my free body diagram that I just drew. Okay? And I'm going to ignore the fact that the y direction is this way because we're not going to use it. You don't really know what to do. You're trying to find the acceleration of the system. So let's apply Newton's laws in all the directions that matter. So let's apply Newton's law in the x direction to this problem and in the y direction to this problem. And in this problem, we'll apply it in the x direction, which is vertically, and see what equations we get. So I'm going to apply Newton's law to the little mass m in the x direction. So the force pointing in the positive x direction is a little mg, minus the force in the negative x direction, which is T, and that's got to equal little m times a. So that's what I get when I apply Newton's law to this problem with the positive x direction being down. So remember, this is the acceleration in the positive x direction, a. All right. Now, I'm going to solve that for T because I want to eventually get rid of the tension because I'm trying to find the acceleration of the system. So if I solve this for T, it looks like that, and I'm going to call that equation 1. Now, let's apply Newton's law to the capital M in the y direction. That's this direction. So the forces in the positive y direction, the normal force, minus the forces in the negative y direction, which is mg, have got to equal 0. That's going to tell us that the normal force equals mg. We're going to need the normal force because we have friction, and anytime you have friction, it's related to the normal force. Okay? Now, let's apply Newton's law to this problem, capital M, in the x direction. So the forces to the right, which is the tension, minus the friction force to the left, has got to equal this m times the acceleration in the x direction. So that looks like that. Now, we're trying to find the acceleration. We have two unknowns here. So for t, we're going to substitute in this expression up here. For the friction force, we know the friction force is mu times the normal force. So instead of friction, I can put in mu times normal force, and that equals m times a. Okay? So now when I substitute in the tension from up here, because I'm trying to eliminate the tension so I can find the acceleration, I get this expression. Here's the tension from equation 1. That's just this. Minus the friction, which is mu times the normal force, but the normal force is mg. We found that up there. That equals ma. So here's a big old equation which we need to solve for a. All right? So I'm going to rewrite it a little bit. I'm going to bring this term to the other side so it becomes positive right here. And that leaves us with mg minus mu mg equals, and on this side I have m plus little m times a. I can then divide both sides by this m plus m right here, and I'll get the following expression for the acceleration. Okay? So once you know the acceleration, you're given the masses, you're given the coefficient of friction, and you know g, of course, so you can evaluate this and you can figure out the acceleration is 1.75 meters per second squared. Once you know the acceleration, you can then go back and find the tension. Here's an example. You could solve this equation. If you know the acceleration, you know little m, you can find the tension. Or you could go here. You know you know mu times the normal force. You know m and a, so you could find t. So it doesn't really matter how you do it. I would substitute back into equation 1 the acceleration I found, and you can use that to solve for the tension. Okay? So in this case, when there's a pulley, you can't just solve it as one big system. You have to break it into parts, and because the tension is the same in the string here as it is here, those tensions T are the same. That allows you to couple the two problems. You can solve one equation for T and substitute it into the other equation and then solve. Okay? So these are more complicated problems. You'll have to be a little bit careful drawing your diagrams. In every case, for every problem, for each component, make sure that the positive x direction is the direction the object accelerates. And that may not be the same for each problem, for each part of the problem. This guy accelerates to the right, this guy accelerates down. So for this guy, the positive x direction is downwards, and for this guy, the positive x direction was to the right. Okay? All right. Good luck. Tackle a couple of those.